a, so they're allowing a multiplier of a. What did they say? Let's see, what number should I use? I don't know. Okay, let's say, maybe I should say, all right, I'll leave it like that. A, I'll say, what letter should I use? A, B, C. Okay, maybe C. No. A, B. Oh, well, I'll use B. A, B to the x. Okay? So they want a function like this. So well, all I'm saying is you need a base and you're allowed a multiplier. Okay? But you want it to go through this and this. Okay? So you're trying to figure out which function will do that. Now, let's see. If I said I just wanted it to go through this point, then I could say, this is, let me write that down, -2, -36. -2, -36. So suppose I wanted it to go through those two, that point. Then how could I arrange that? I just say, well, this is the y value, right? And this is the x value, right? So I just put the x value in here and the y value in here and solve and figure out what a or b has to be, right? Okay, so let's write that down. So this has to be true. Sorry. This has to be true. -36 has to equal a, b to the -2, right? That's what it means for it to go through this point, right? Okay, but that doesn't seem like it's going to give us... There's probably a lot of a's and b's that make this work. Okay? There's probably a lot of a's and b's that can get this to work. But that's not the only condition. Okay, what other condition? I'm sorry. 4.5, comma 1. Has to also go through that, right? So that means that it also has to satisfy -4.5 equals a, b to the 1. Okay, so it has to satisfy both of these. So that might be enough to single out a particular a and b. Right? That might be enough conditions to single out a particular a and b. Does everybody know how I wrote these two equations? Right? If it has to go through this point, that means it has to satisfy this equation. Right? Everyone see that? Yes? No?
Sir, why would you write -1 after the...
Oh, okay, thank you. Okay, now does everyone see it? Right, it has to satisfy this point, that's y, -2, and it has to satisfy this point. Okay, does everyone agree? So this might be enough to have just a single solution. Because before, if we just had one equation, there are probably many solutions, many combinations of A and B that would work. Just like, when you have x plus y equals 10, okay, and I say, is that what I want? And if I say x has to be equal to, no, sorry, that's not a good example. I'm not sure what I'm trying to say. But, sorry. If I say x has to equal, if I ask you what are the solutions to this, how many solutions are there? Just x plus y equals 10. How many solutions are there? How many solutions? Well, x could be 2 and y could be 8. X could be 3 and y could be 7. So how many solutions? There's an infinite number of solutions, right? We didn't narrow it down enough. If I gave you two equations like x plus y has to equal 10 and x plus 2y has to equal 4, now probably there's only one solution to this, right? Because this is a line, this is another line, and they intersect just in one place. So there's only one solution, right? So when you give two conditions, you're probably narrowing it down to a single solution. The same thing here. There are two variables, a and b. If we just give one equation, probably there are many solutions to it. But when we give two equations, there's probably just one solution to it. Okay? So now our task, though, is to figure out the solution. So if it would look like this, I think everybody would know what to do. Right? How to find the solution, right? Everybody knows how to do that, right? You know what to do there. Okay, what can we do here? Well, there's a nice trick, which is, since this equals this, and this equals this, if we divide this by this, it should be equal to this by this. Right? Does everyone agree with that? Right? So that says that this should equal this. Does everyone agree with that? Okay, so what does that give me? Gives me this thing should equal what? The A and the A cancel, right? So that's the, over here we wanted to cancel one like X, and then you could solve for Y, right? That's the standard way. So, same thing here, we'd like to cancel one of the variables, and this does it, right? So now we cancel A by A, and what do we get? I get b negative 2 over, so I think that's b to the negative 3. Is that true? I think that's right. So I get this number equals b to the negative 3. Okay, so then we should be able to figure out what b is. Okay, once we figure out what b is, then we can also take either one of the two original equations and figure out what a should be. Okay? So then we get the a and the b, and then we know the answer. So the question was, find the equation for an exponential function that passes through these 2 points. We should be able to give that. Okay? So I'll let you finish that yourself. So the point is, if you have just one point, there are going to be many solutions for a and b. But when you have two, you're probably going to have just one possible pair of a comma b that will work. Okay? Okay, next one. Find the equation of the exponential function that passes through the pair of points given below. It's the same process again. Okay? Any questions about those? Okay. All right, then we talked about exponential functions now. Okay, the next section of problems is on logs. So now we have to talk about logs. So let's, I want to talk about what's meant by inverse functions. Okay, inverse functions. Okay, so two functions are called inverses. Sorry, before that, I need to do something else. Okay, let's take two functions. F equals x squared, and g equals x plus 8. Okay, so we can talk about f plus g. We can talk about f minus g. We can talk about f times g. We can talk about f divided by g. So f plus g is what? Okay, that's f plus g. Okay? So if I wanted to know, I could call that. Okay, now that notation is a little bit confusing, right? Looks like it's like f plus g of x, but that's not. I want f plus g as a function. So I want somehow to indicate that this is the name of the function, f plus g. So sometimes they do that. Okay, just to indicate that that's the name of the function, and then you put x into it. Okay, so if I wanted to know what's f plus g of 2, that doesn't mean times 2. Okay, it means of 2. So what is that? So it's 2 squared plus 2 plus 8, right? Okay, everyone understand that? Right, so anyway, that's what? 14. Okay? Alright, so that's what f plus g means. What's f minus g? X squared minus x plus 8. Okay? What's f times g? Right? And what's f divided by g? Right? And, if you want to do notation for this, I'd probably do this. Okay, so that otherwise, anyway, that's, okay? Okay, now, there's one other, these are called operations. So addition, subtraction, multiplication, and division. There's one other, and these are operations on functions. Usually there's operations on numbers, but here they are operations on functions. And there's one other operation on functions, and that is this. Okay, so what does that mean? So, okay, let's just make sure that is clear. So if I ask you, what is f of 1? What's the answer? So f is x squared, so it's 1 squared, right? Right? F is that. Okay, so that's 1 squared. If I ask you, what is f of 2? It's 2 squared, right? If I ask you, what's f of 3? 3 squared, right? And if I ask you, what's f of a? A squared, right? And if I ask you, what's f of b? B squared. So what does f say to do? Whatever you put into f, you should square it, right? That's the rule for f. Okay? So, if I ask you, what's f of a plus b, you should still follow the rule. So if you do it very simply, you would just say, oh, it's a plus b squared. Right? It's the same rule. Whatever you put in, you should square it. Okay, it wouldn't be a squared plus b squared. Right? It's the whole thing squared. Right? And if I asked you what's f of a plus b plus c, it would be what? Okay, you don't have to think at all. Right? There's no thinking, it's just simple. Okay? Alright, so whatever you put in, you're supposed to square it. That's the rule for f. If the rule had been cubed, then it would be whatever you put in for f, into f, you would cube it. Okay? Alright, so anyway, so if I ask you this, just follow the same rule. What's the rule? Whatever you put in into f, you just square it. So just make it really simple. Just write it as g of x squared. I didn't even have to think about it. Okay? But what is that? Just replace g of x now. What do you get? What is g of x? So it's x plus a squared. Okay, so that's what this is. Okay? And we could do another one. I could say, what about this? But before we do that, if I just ask you, what's g of 3? So it's 3 plus 8, right? If I ask you, what's g of 5? 5 plus 8. I ask you, what's g of a plus b? A plus b plus 8. Right? Right? So if I ask you what's g of f, you don't think at all. You just say what? F of x plus 8. Right? Okay, now you can replace f of x by x squared. Get that, right? Everybody agree with that? Okay, so then are these equal? So this one was what? Over there. X plus 8 squared. And this one was what? X squared plus 8. I don't think that they're equal. Right? So this is not the same as this. I mean, it might be sometimes, but in general, it's not the same. Right? So, okay? Now we have this kind of symbol for this, and the symbol is F circle G. Okay? So, I guess we'll do this again. Okay? So that's the symbol for doing this. So if you want to, this just means do this. Just like this just means, add the two functions. Right? Okay, so this just means do this. And so what's the symbol for this one? What's the symbol for this one? Okay? Right? So this is an operation also, and this operation is not called addition, and it's not called subtraction, it's not called multiplication, and it's not called division, so we need another name for it. It's called composition. Okay? So composition means doing this. This one means doing this. Okay? It's another operation. Now, these operations we can do with numbers, right? You can add numbers, you can subtract them, you can multiply and divide them, but, there's no such thing as doing this with numbers, right? There's no analogy for numerical operations for this operation. Right? But that doesn't matter. It's still an operation for functions. Okay? So this operation is called function composition. Function composition. Okay? Everyone understand function composition? Okay. Now, I think you've probably done that before, but I thought I'd better review that. So now, I want to talk about what I mean by two functions are called inverses of each other. Okay, so what does that mean? That is going to mean, two functions are called inverses of each other if you do one and then you do the second one, it's like having done nothing at all. Okay, it's like you'd put x into one, and then you put that into the result of that into another function, and you get back x again. So nothing happened. Okay? All right, you understand? So can anybody think of an example? Okay, here's an example. If I square a function, and then I take the square root, then I get nothing. Nothing has happened. Right? So those two functions, squaring and square root, are called inverses of each other. Okay? Or if I cube a function and take the cube root, those two would also be called inverses. And of course, if you do it in the other order, it's still going to work. That is, if I take the square root and then square it, that's also, right, doing nothing. Okay? So this pair of functions, squaring and squaring and square rooting, are called inverses. Okay? Or cubing and cube rooting are called inverses. Okay? Can we think of another? Anyway, let me write. So if g of x equals x squared and k of x equals the square root of x, then we'll say g and k are inverses of each other. Because when you do them together, then nothing happened. And what do I mean by doing them together? I don't mean adding them together. Right? If you add these together, you don't get x back. What do I mean by doing them together? I mean, if you do this, k of g, that's what I mean by doing them together, right? Putting one inside the other. Right? So when you do the composition of the two of them,